HCl will be also formed as a byproduct which can be removed using pyridine. Dilute nitric acid means you're going to get two products. One will be orthonitrophenol, another one will be paranitrophenol. Intermolecular hydrogen bonding, which causes the association of molecules. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 7 of the chapter Alcohols, Phenols and Ethers. So in the last session we studied physical as well as chemical properties of phenols, right? We started with the chemical properties of phenols. So in today's session we are going to continue with that. That is esterification of phenols, acylation of phenol, electrophilic substitution reactions of phenols, which includes nitration, halogenation, Kolb's reaction, Raymond-Tiemann reaction, a reaction of phenol with zinc dust, oxidation of phenols. All of this we are going to complete in this session. By next session we will be starting with the last part of this chapter, that is ethers. Okay, right. So beginning with the first reaction, that is esterification of phenols. Esters are produced when phenols are heated with carboxylic acid in the presence of acid catalyst. So here also we have already studied it in alcohols, that is the esterification. So instead of an alcohol, we are going to take a phenol. So that's a difference in this reaction. So phenol will be taken, it will be made to react with carboxylic acid. What you are going to get? An ester will be formed with water as well, right? So we are using acid catalyst here and this reaction is called as esterification. So the function of the concentrated sulfuric acid is to act as a protonating agent as well as a dehydrating agent. So the reaction proceeds in an acid catalyst, that means concentrated sulfuric acid or HCl we are going to use. This is because it acts as a dehydrating agent. As I told, water will be removed, right? So for that, concentrated sulfuric acid is used as a dehydrating agent, okay? As well as a protonating agent means it is able to donate its H+. So we can see here an acid is taken, general representation RCOOH, right? Okay, to which phenol is added. So C6H5 stands for this part, right? This is your phenol. So this is C6H5, the benzyl part is C6H5. One hydrogen is being replaced by hydroxyl group. No, so this is C6H5OH which is shown here. C6H5OH. So that is your phenol. So from hydrogen from phenol and the hydroxyl group from carboxylic acid will be removed as water. H2O will be removed. Now what is left there? RCO. C6H5. So the C double bond O, what is that? It is ester, right? RCOO C6H5. That will be formed. That is your ester. So let's take a specific example here. Benzoic acid. Okay, that is benzoic acid means on benzene you have a carboxylic group COOH, to which we are adding phenol. So what happens again? Hydrogen from phenol and hydroxyl group from carboxylic acid will be removed as water. So what you are going to get on benzene, you will have COO, that is this part and this part will combine together, right? So again you are going to get an ester, C double bond O. This is ester and the C6H5 from the phenol. So this is simple, we have already studied in alcohols as well. Now, esters can be also obtained by treating phenols with acid chlorides or acid anhydrides. So, this process is called as acylation, that is we are going to add an acyl group. So, in that way also we can form esters, right? So, esters either it can be formed by reacting phenols with carboxylic acid or else it can be obtained by treating phenols with acid chloride or acid anhydride. So, first we are going to see acid chloride. So, what is acid chloride? RCOOH is your carboxylic acid. So, the hydroxyl group will be replaced by chlorine. So, what you are going to get? RCOCl. So, this is called as your acid chloride. Okay. So, this is phenol reacting with acid chloride. So, it is shown here R dash to mention that this alkyl group and this alkyl group is different. That's it. Okay. So, what you are having? RCOCl. So, C6H5OH and R dash COCl you are having. So, this happens in presence of pyridine base so as to neutralize the HCl which is formed during the reaction. So, HCl will be also formed as a byproduct which can be removed using pyridine. Okay, it will neutralize the acidity due to the HCl. So, what happens here as told, this hydrogen and chlorine, HCl will be removed. Okay, so HCl will be removed. Then what is left behind? You have C6H5O and R-CO. So how can I write this? It will be C6H5 and you have O from here and CO from here. So we can write C double bond O and what is there? R dash also is there, right? So this is your ester which is being formed. So we have taken phenol here and acid chloride. Which acid chloride? Methyl acid chloride we have taken. That is the alkyl group is CH3. Now what happens? This hydrogen and this chlorine will be removed as HCl. So you have C6H5O and you have CH3CO, right? So C6H5O CH3. Okay, so you can write it as OCO also or else COO as well. So this is your ester. So you have to remember this carbon oxygen bond which is shown here is actually a double bond, right? Okay, now another method was also discussed. One, it is by the addition of acid chloride RCOCl. Next one is by acetylation, can also be done by treating phenol with acetic anhydride, can be also used to form ester. So that means three methods we have studied here. One is reaction with carboxylic acid, one is reaction with acid chloride, next one is reaction with acetic anhydride to form an ester. Let's see. So this is salicylic acid, okay, that is you have your phenol and the carboxylic acid is present. Acetic anhydride. Now what is acetic anhydride? CH3CO, CH3CO, and it is bonded by an oxygen atom. So now what happens on this phenol? What is there? This hydrogen atom is going to be replaced by one CH3CO group. So this hydrogen is being replaced by CH3 group. Okay. So already one oxygen is there. Okay, already one oxygen is there and the COCH3 will be bonded here. I hope it is clear. Now what is there? One more molecule is there, right? CH3COO. This much part is remaining, CH3COO, and the hydrogen is being removed, right? So that will combine together and form CH3COOH. I hope it is clear. So the hydrogen which is being removed from here mix up with the CH3COO and form CH3COOH, and now, once the hydrogen is gone, you have only the oxygen, right? That oxygen and this much part, CH3CO. So, this is called as your acyl group, CH3CO. Acylation is taking place. So, that can be happening there. So, you will get an ester. So, what you are getting? Aspirin, which is an ester, right? I hope it is clear. Moving on to the electrophilic substitution reactions of phenols. So, again, electrophilic substitution reactions means electrophile. What is electrophile? Which is having attraction towards electrons, that is negatively charged species. So it itself will be positively charged, right? So phenols is more reactive towards electrophilic substitution reactions than benzene. Okay, this is because of the hydroxyl group which increases electron density in benzene ring by donating the lone pair of electrons on oxygen atom to the OH group. Moreover, it is stabilized by resonance. Okay, so why they are showing? That is when you are comparing phenol and benzene. Benzene is without the hydroxyl group, right? And phenol and benzene, if you are comparing, phenol will be having more reactivity towards electrophilic substitution reaction because resonance is taking place. That means in phenol, the oxygen atom is having lone pair of electrons which will undergo this resonance. So what will happen? This resonating structure we have already discussed in the last session, right? So this electron pair will be shifted here. It becomes a double bond here and the oxygen will get a positive charge. And this bond makes the charge here. Now the charge becomes the bond becomes the charge which is shown here. Now this charge becomes a bond here and the bond becomes a charge here. Now the charge becomes bond here again and this double bond is shifted back to the lone pair. So this resonating structures is happening. That is why it is more stable and more reactive towards electrophilic substitution reaction. It is clear from the above structure, carbon atoms at ortho and para positions acquire negative charges. As a result, electrophiles attack these positions to form ortho and para derivatives. So, what you can remember, because the resonating structure shows negative charges in the ortho and para position. You can see this is one ortho, this is para, this is another ortho. So, negative charges you are getting in the ortho and para positions. Because of that, when electrophilic substitution reactions is going to happen, the substituent which is going to be substituted, it will be substituted in which position? Of course, the ortho and para position, right? So, let's begin with the first reaction, that is nitration. With dilute nitric acid at low temperature, phenol gives a mixture of ortho and para nitrophenol. So, ortho will be present only 15%, rest will be para nitrophenol, because already we have discussed para products will be more stable because it is more symmetric. So, phenol in presence of dilute nitric acid HNO3, what you are going to get, as discussed already from the resonating structures, in ortho and para position you have the negative charge. So one you will get an orthophenol, that is one product will be orthonitrophenol, another one will be para-nitrophenol. So this is 1, 2, 3, 4, this is your ortho position, this is your direct opposite is your para position, right? And water will be removed. Okay, so what happens here? Orthonitrophenol and para-nitrophenol is formed. I hope it is clear. Now the ortho and para isomers which is formed, both of these are formed, right? So this can be separated by steam distillation. So this is also an important point, which is the distillation method, or which is the separation method which is used to separate ortho and para-nitrophenol. So which is the method? It is steam distillation, right? So orthonitrophenol is steam volatile. Orthonitrophenol is steam volatile due to intramolecular hydrogen bonding, while para-nitrophenol is less volatile due to intermolecular hydrogen bonding, which causes the association of molecules. Okay, so this is your orthonitrophenol. Intramolecular hydrogen bonding is taken place. So as you can see, this is the phenol and this is the nitro group, NO2, and you have OH. So oxygen negative charge and hydrogen positive charge, there will be a bond formed here. So this is formed within the molecule. So this is intramolecular hydrogen bond, right, within the molecule. So because of this, it is steam volatile. It is steam volatile. That is, it is more volatile. So you can, this orthonitrophenol can be separated through the steam. Now you have para-nitrophenol. That is, you have the one hydroxyl group is here, nitro group is here. This is another molecule of nitrophenol, right? So you have the OH here and NO2 here. So the hydrogen and oxygen from two different molecules of para-nitrophenol will form a hydrogen bond here. So this will be intermolecular hydrogen bonding which is formed here. Because of that, it will be less volatile. So this is how you can separate ortho and para-nitrophenol through steam distillation. I hope it is clear. Now, next method. One method was using dilute nitric acid. In ortho and para position, nitro groups will be substituted. Next method is with concentrated nitric acid. So instead of dilute nitric acid, we are going to use concentrated nitric acid. Phenol will be converted to 2,4,6 trinitrophenol, which is called as picric acid. So this is important to remember. Dilute nitric acid means you're going to get two products. One will be orthonitrophenol, another one will be para-nitrophenol. If you're using concentrated nitric acid, what is going to happen? You will get in both the ortho position and para position. In all the ortho and para positions, the nitro group will be substituted. So this is called as picric acid in the common name. So if you are numbering 1, 2, 3, 4, 5 and 6. So 2, 4, 6 trinitrophenol is called as picric acid, and it is a yellow colored crystalline solid. Okay, so industrially picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it into phenol 2,4-disulfonic acid. This yields picric acid on treating with concentrated nitric acid. So industrially, when you are preparing directly, we are not using concentrated nitric acid. First we are going to use concentrated sulfuric acid, which then reacts with concentrated nitric acid to form the picric acid. So I hope the difference between nitration, that is when you are using dilute nitric acid and concentrated nitric acid, is clear for you. Now next one is halogenation. So what does halogenation means? We are going to substitute what? Halogen, right? In aqueous medium, halogenation takes place at the available ortho and para position, resulting in a tri-substituted product. For example, when phenol is treated with bromine water, a white precipitate of 2,4,6 tribromo phenol is formed. So phenol reacts with bromine. What happens? In both the ortho and para position, bromine will be substituted. So of course, this is 1, 2, 3, 4, 5, 6, 2,4,6 tribromophenol will be formed. In aqueous medium, phenol ionizes to give phenate ion. The presence of negative charge on the oxygen atom activates the ring to a large extent towards electrophilic substitution reaction, resulting in charge substitution. What does that mean? This is your phenol. So, in presence of water, which is shown here, in presence of water, your phenol will be dissociated into phenoxide ion, right? Phenoxide ion by the removal of H plus. So this phenoxide ion is going to get activated because it is having a negative charge. What happens? The bromine will get attached in both the ortho and as well as the para position. So you are going to get a tri-substituted product here. Now the next one is in non-polar solvents such as CCl4 or CS2, that is carbon tetrachloride or carbon disulfide. The halogenation becomes slow and only one halogen atom is introduced at either para or ortho position. Thus a mixture of isomeric products is obtained. Okay, so again, like in nitration here also, if you want to get a mono-substituted product, you use CCl4 or CS2. If you need a tri-substituted product, what you will be using? It will be bromine water, right? So here also in presence of carbon disulfide or CCl4, we are going to add bromine. What happens? You will get ortho-bromophenol and para-bromophenol, right? So in non-polar solvent, phenate ion is not formed, okay? This means that the activation of the ring gets suppressed since the oxygen has no negative charge. As a result, a hydroxyl group donates the electron pair to the ring only to a small extent and mono substitution will only take place. So here phenate ion will not be formed, but in the case of the first reaction, phenate ion will be formed. The next one is Kolb's reaction. So on reaction of sodium salt of phenol with carbon dioxide gas at 413 Kelvin and a pressure of 6 to 7 atm, sodium salicylate, first sodium salicylate will be formed, which on acidification yields salicylic acid. So this reaction is called as Kolb's reaction. This is very important reaction as it is a named reaction. So first what happens? Phenol is going to react with sodium hydroxide and you are going to get sodium phenoxide. Okay, that is sodium will be substituted here, hydrogen and OH will be removed as water. Okay, so this we have already discussed in the chemical properties of phenol, right? So first what will be formed? Sodium phenoxide will be formed. Now to this sodium phenoxide, what we are adding here? Carbon dioxide is going to be added. So now what happens? In this position, that is your ortho position, one hydrogen atom was already there, right? So that hydrogen atom is going to be shifted here and it forms OH here. Now what happens? The Na plus will be shifted to the ortho position and already your CO2 will be also added to the ortho position. So this is your CO2 and Na plus which is present here. Okay, now what happens? Acidifying it. Once sodium salicylate is formed, we are going to acidify it. That means H plus is going to be added. Now what happens? H plus is added means you already have COO minus. COO minus is already there. So H is added means you're going to get COOH, right? COOH will be formed and already the OH is also there. So I hope it is clear. So this is called as IUPAC name. If you are seeing, it will be 1, 2, 3, 4, 5, 6. So it is on the second carbon atom you have a hydroxyl group. You can't name this as the second, you can't number this as a second carbon atom because carboxylic group is the highest priority. So this will be 2-hydroxy, yes, 2-hydroxy benzoic acid, which is commonly called as salicylic acid. So this is Kolb's electrolysis. So first sodium phenoxide is formed by reacting phenol with sodium hydroxide. Then carbon dioxide reacts to it and from sodium salicylate, which on acidification, that is addition of H plus, will give you salicylic acid. So if the question asks you what is the preparation or write the preparation of salicylic acid, this is a reaction that you can write. Okay. So the next one is Riemer-Tiemann reaction. Again a named reaction. So it is very, very important. So when phenol is heated with chloroform. So what was chloroform? CHCl3, right? Chloroform in the presence of sodium hydroxide, followed by hydrolysis, orthohydroxybenzaldehyde, that is salicyl aldehyde is formed. This reaction is known as Riemer-Tiemann reaction. So in Kolb's reaction, you are getting salicylic acid. In Riemer-Tiemann reaction, you are getting salicyl aldehyde. Okay. So phenol is taken, reacted with chloroform and aqueous sodium hydroxide. So what is going to happen? Again, sodium phenoxide will be formed and what happens? From the chloroform, CHCl2 will be substituted in the ortho position. Okay, that means HCl will be removed from here. That is, you have one hydrogen here and out of the Cl3, one Cl will be removed as HCl. What will be present here? CHCl2 will be substituted in the ortho position. So this is the intermediate compound which is formed, to which we are going to add sodium hydroxide again. So what you are going to get? It is going to CHO OH twice will be obtained here. 2 moles of sodium hydroxide and again we are going to add means the Cl2 will be replaced by 2 OH, right? So that is shown here. So now in the next step, we are going to remove the water. H2O is going to be removed. So H2O is removed means this is OH twice, right? OH twice. So H2O is removed means one oxygen will be still remaining there. So you have the aldehyde which is formed here, CHO. In the next step, you are going to add HCl. HCl if you are going to add means this hydrogen will be attached with the O minus and form OH and the Cl will be removed with the Na plus. So this Na plus and Cl will form NaCl which will be a byproduct and you are getting OH and CHO here. So this is your salicyl aldehyde. So this is Riemann-Riemann reaction. So which is the reagent that we are using in Kolb's reaction, Riemann-Riemann reaction, all of that are also important. So in Riemann-Riemann reaction, first chloroform and sodium hydroxide, what is going to happen? CHCl2 will be substituted here. Then again we are going to react it with sodium hydroxide. What happens? Instead of CHCl2, you get CHOH twice. Then water will be removed means you are going to get an aldehyde here. Then O minus Na plus is there. So we have to just remove the Na plus. So we add HCl so that the hydrogen will be substituted there. You get the salicyl aldehyde. The next one is a reaction of phenol with zinc dust. Okay. So phenol when it reacts with zinc dust, what happens? You get benzene and zinc oxide. So this is a very simple reaction as well as a very important reaction. So what happens? Nothing is going to happen to the double bonds. Only this hydroxyl group will be removed. That's it. Okay. So what you are going to get? Benzene will be obtained. So how you can obtain benzene from phenol? If that's a question, how you can obtain benzene from phenol? By reacting it with zinc dust. Right. So the next reaction is oxidation of phenol. So the first one is oxidation of phenol by chromic acid forms benzoquinone. So chromic acid, a mixture of K2Cr2O7, potassium dichromate and potassium sulfate. Right. So it forms benzoquinone. This is a structure of benzoquinone. So quinones are not organic compounds. They are alpha beta unsaturated ketones. So you have phenols which reacts with chromic acid. What happens? Yes, on the para positions you will have 2 double bond. It's a ketone which is formed. Alpha beta unsaturated ketone will be formed. So benzoquinone is formed by the oxidation of phenol with chromic acid. Next method is in the presence of air, phenols are slowly oxidized to pink colored mixtures containing quinones. Okay. So here also you are getting benzoquinone by reacting it with air. Okay. So next one is uses of phenols. So phenols are used as a powerful antiseptic in soaps, lotions, etc. in the manufacture of bakelite, condensation polymer of phenol and formaldehyde. Bakelite is a polymer which is a condensation polymer of phenol and formaldehyde. Next is it is used in the manufacture of Dettol, in the manufacture of pharmaceutical products such as salicylic acid and aspirin. See, we have already studied the reaction how to prepare salicylic acid as well as aspirin, right? So that and all is formed from what? Phenols itself. Now the last one is in the manufacturing of dyes like phenolphthalein, picric acid. Phenolphthalein, we have used it in our labs as well. It is an indicator, right? So in the preparation of this, phenols are being used. Okay. So in the next session, we are going to start with ethers. So again, we'll be starting with an introduction to ether, classification of ether and the nomenclature of ether we'll be discussing in the next session. So I hope the concepts that I've covered in this session is clear for you. So that's all for today. Thank you.